For our other trig integrals, we are going to look at what to do if we are asked to integrate some sort of combination of tangent and secant or cotangent, cosecant. Now, we're going to talk about these at the same time because the patterns that we see in their derivatives are exactly the same. So just as a reminder, let's get our derivatives written out. Because these are going to be really important when we decide which u substitution we're going to do. All of these are always going to lead to a u substitution, just like we saw with sine and cosine. With these functions, though, tangent, secant, and cotangent, cosecant, it's not as simple as just looking to see whether you have even or odd powered functions to work with. So the derivative for tangent is secant squared, so we want to remember that. And the derivative for secant is secant tangent. Now cotangent and cosecant, their derivatives have the exact same pattern. The derivative for cotangent is negative cosecant squared. So really the only difference is that for cotangent and cosecant you're going to see negatives in front. The derivative for cosecant is negative cosecant cotangent. So you see this exact same pattern. The derivative for the tangent is the secant squared. Derivative for secant is secant tan. So it's self and the other guy. Same thing down here for cosecant. It's self and the other guy. The only different tangent or cotangent and cosecant have the negatives. So our approach for these antiderivatives are going to be exactly the same. And like I said, we can't just rely on whether we see even or odd powers to do it. We're going to think more ahead to which u substitution could we possibly make in order for this to work. We also want to keep in mind our Pythagorean identities in case we have to switch between any of these two functions. So remember, tan squared plus 1 equals secant squared. And then 1 plus cotan squared, it really doesn't matter what order those two terms are in, equals cosecant squared. So the key with these working these antiderivatives is always to have your u substitution in mind. You always want to see which derivative you are capable of holding on to, and then if you can hold on to that derivative, is it possible to get all of the other expressions and factors in the integral written in terms of what your u would be to match that derivative. So always have the du, I'm just going to say u substitution in mind. Which means we always need to be thinking about these derivative relationships. We're still going to be using our Pythagorean identities to switch back and forth. So as an example, if we were asked to integrate tan squared x times secant squared x, we've got two options, and as you're first learning this, it might be helpful to write out your two options. Always think with the u substitution in mind. If I were to do a u substitution and pull my du back in, remember trig functions always have another, when you take the derivative, is always another trig function. So we want to think about which possible u substitution could we do and have the du in there ready to cancel out. So if I were to do a u substitution for tan, that means I would need to make sure that I hold on to a secant squared, and I would want all of the rest of my functions written in terms of tangent. That way I could do a u substitution for tangent, and the du would cancel off the secant squared. So this one works out perfectly that way. We're going to do a u substitution for tangent. We're just holding on to that secant squared, and it will be canceled out later when we bring back in the du, because we have to keep in mind the derivative for tangent is secant squared. It's always good to write out your other option. Sometimes both ways will work, and one way might be easier. The other option is to hold on to a secant tangent. If we were to do a u substitution for secant, we would need its derivative in there to cancel later when we brought the dx substitution back in with the du. So the derivative for secant is secant tan. So I would have to hold on to a secant tan. And if I did this, what I would have left over compared to my original integral, remember my original integral was tan squared secant squared. I'm holding on to one of each of them. I would have one of each left over. I would still have another secant to deal with and another tangent to deal with. And when we look at that, we want to ask ourselves, is it possible to get everything except for what I'm holding on to for my u substitution to work to be written in terms of secant? And in this case, it is not, because all I have is a single tangent. And if you remember back to our Pythagorean identities, we can only switch over squares or multiples of squares. So this way is not going to work, this second way, because we cannot switch a single tangent function into a secant function. So that way is not going to work at all. So our only option here is to hold on to a secant squared and do a u substitution for the tangent. So that's how we're going to work it. So I'm going to say that the integral for tan squared secant squared, I'm going to do a u substitution for the tangent, and then du is the derivative for tangent is secant squared. And if you want to, you could divide your secant squared over so you can see how it will cancel when you pull it back into your integral. So now we're going to replace all the tangents with u, and we're going to replace dx with 1 over secant squared du, and see what happens in our integral. So all of the tangents are going to be replaced with u, so that's u squared. And then I haven't said anything about this secant squared yet. We'll see what happens with that in a minute. But the dx is going to be replaced with 1 over secant squared du. And just like we planned out from the beginning, those two guys will cancel. And then all we're left to integrate is u squared, which is a simple power rule. So we get 1/3 u cubed plus c. And to finish it off, we go ahead and replace our u with tangent. So when we do these problems, we always have to keep the u substitution in mind. So we always first check for the derivatives. We check to see which derivative we can hold on to. And then once we kind of partition that off in some parentheses, we're going to look to see what we have left over and see if it's possible to get everything left over written in terms of its antiderivative function so that the u substitution will work. So let's take a look at another one. And for this one, I'm going to do cosecants and cotangents. The pattern is going to be exactly the same. The only difference is the derivatives and antiderivatives have negatives. Now you don't need to account for those when you are originally checking the problem for derivatives, because the negative is just a coefficient, and it's perfectly fine to pull that negative back in with your u substitution and then just move it to the front and deal with it at the very end. So for this next one, let's look at cotangent x, cosecant cubed x. we want to see if we can find the antiderivative for that function. So just like I did before, I'm going to write this both ways and see which derivative I can hold on to and make my u substitution work out successfully. Even if I recognize the first way is going to work, I'm still going to go ahead and write out the second way. It's possible that the second way is going to be a lot easier. So if we were going to do a u substitution for cotangent, the derivative of cotangent involves cosecant squared. So we would have to make sure that in the process of doing this u substitution, that there was a cosecant squared in there that could cancel when we brought the du back in. So I'm going to look at my original problem. I'm going to pull off a cosecant squared and write what I have left over. Now, if I'm holding on to a cosecant squared and I'm doing a u substitution for cotangent, that means I want everything in this problem to be written in terms of cotangent except for the piece that I've already designated I'm going to hold on to. And we want to know if that's possible. Well, this one's already cotangent, so that works. Can we write cosecant in terms of cotangent? And remember, the only way that we're doing this is with our Pythagorean identities. Pythagorean identities involve trig functions with squares on them. That cosecant does not have a square. We are not going to be able to rewrite that as a cotangent. So this way is not going to work. So let's try our other way. If we do a u substitution for cosecant, the derivative for cosecant involves a cosecant and a cotangent. So I want to make sure I hold on to a cosecant and a cotangent. Compare that to your original integrand and see what you would have left over if you pulled those two guys out. So I'm pulling off one of the cosecants and I'm holding onto the cotan. That means I still have cosecant squared left. So this expression is equivalent to my original integral. So if I'm holding on to cosecant cotangent, I'm doing that because I want to do a u substitution for cosecant. That means I want the rest of my integrand to be in terms of cosecant. And it is. It already is. We don't even have to do any Pythagorean substitutions. So this way works, and it's ready to go right now. It's ready for u substitution. We don't even have to do any rewriting. So the way that we're going to work this problem is we're going to hold on to a cosecant cotangent. And don't do anything with that yet. We're just holding on to it so that our u substitution will work. We're going to do a u substitution for cosecant because this is the antiderivative, or excuse me, that is the derivative for cosecant. So we're going to say u equals cosecant. And then remember, du is negative cosecant cotangent. And if we pull that over as a fraction, so we can actually witness the canceling, dx is going to get replaced with negative 1 over cosecant cotangent du. So we'll use our u, and we'll use this dx to do our substitutions. Don't do anything with the piece that you have partitioned off. That hopefully will cancel on its own. I did say that I'm going to let u equal cosecant. So this piece ends up as u squared. And then the dx is going to get replaced with negative 1 over cosecant cotangent. And it works out nicely that this cosecant cotangent cancels with this one, but we still have the negative. So that's really the only difference that we see with the cosecant cotangents compared to the secants and tangents, is that negative sign. The derivatives and antiderivatives are in the exact same pattern, but the derivatives for cosecant and cotangent are negative. So we just have to integrate u squared. And we have our negative in front. So I've got negative 1/3 u cubed plus c. And our u, we said, was cosecant. So to finish this off, we will just rewrite this back in terms of trigonometry. So our final answer for the antiderivative of cotangent cosecant cubed is negative 1/3 cosecant cubed. And let's try one more of these, and I'm going to make sure that we actually have to do some substituting this time. For the next one, we are going to try to find the antiderivative of tangent cubed. And this one can be a little bit tricky because our two options for our derivatives, if you look back, both of these derivatives contain secants, and we don't have any secants in our integrand at all. I can't even start to hold on to one of my derivatives to see which u substitution is going to work because I don't even have either of these derivatives available. So just to be able to start this problem, we need to go ahead and switch some of those tangents over to secants at the very beginning. Now remember, we do this with Pythagorean identities, and Pythagorean identities always change over squares. So I'm going to split that tan cubed up into a tan and a tan squared. That is equivalent to a tan cubed. And then I'm going to replace tan squared with what it's equivalent to in its Pythagorean identity, which happens to be secant squared minus 1. If you look back at the Pythagorean identities that we listed out, we want to solve the tangent secant identity for tangent. In order to do that, we'll have to subtract the 1 over to the right-hand side. So that means I can replace tan squared with secant squared minus 1. So now this becomes tan x times secant squared x minus 1. And because it's got two separate terms, we're going to want to go ahead and distribute. All the problems we've looked at so far have only had one term. They've had multiple factors, multiple things being multiplied together, but it's only been one term, no addition or subtraction. So I'm going to go ahead and distribute this, and we can look at each term individually. So I've got tangent, oh, I'm missing my x. Tan x times secant squared x minus tan x dx. And we really could look at this as two separate integration problems. And we're probably going to have to because we're going to integrate them differently. So we've got to integrate tan x secant squared x dx and then minus the integral of tan x dx. And I'm writing them separately because I know that I'm going to have to do them differently. Now, tan x times secant squared, we can, now that we've got some secants in there, we can evaluate which way is going to be better. If I do a u substitution for tan, the derivative is going to be secant squared, which means I'm going to want to hold on to the secant squared. And I'm going to want everything else in that integral written in terms of tan. And it is. The only other thing in that integral is a tangent function. So it'll work. It's already ready to go. The other option would be to do a u substitution for secant. And the derivative of secant is secant tangent. If you compare that to your original, the only thing I have not used yet is a second secant. Now, secant tan is the derivative for secant. I would be holding on to a secant tan because I'm doing a u substitution for secant. So I want to make sure that everything else that I have left in that problem can be written as a secant, and it already is. I have the only thing I have left is a secant. So in this case, both methods work, and it's really up to you how you do it. Now you are going to get a different answer. One answer is going to have tangents in it, the other answer is going to have secants in it. But just like with the sine cosine problem where they both had odd exponents and we got to choose which one to separate, they're equivalent answers. Both answers are perfectly correct. So it's completely up to you how you want to do it. I personally just think this one looks easier. So I'm going to go ahead and do a u substitution for tangent. And then du is going to be secant squared. Now, I've always been dividing over whatever I had with my secant squared, but that's not entirely necessary. You could recognize that an entire chunk of your integral can be replaced with the du. So if you have a secant squared x dx, you can replace all of that with du. And we do. So secant squared x dx is equivalent to du, and tan x is equivalent to u. And remember, this was just the first part of our integral. We also had to integrate tan x. That is a completely separate integration problem, and that one is not going to be done with the same u substitution setup. And in fact, on page 527 in our textbook, there are some integration, excuse me, let me close that, there it is. There are some integration tables for tangent, cotangent, secant, and cosecant. They don't turn out nicely. They all turn out to have logs in them. You don't necessarily have to memorize them. I'm going to be posting on our Moodle page a reference sheet of integrals that you could use. And anything that's not on that sheet, then you are expected to learn how to use the integrals on that sheet and the techniques that we learned in this chapter to figure out the antiderivatives. So the first one is just a simple power rule. This is u to the first. So we get 1/2 u squared. And for that one, we did it u equals tan. So this is 1/2 tan squared. The antiderivative for tan, if you look on page 527, is negative natural log of cosine. That one's actually pretty easy to do by hand because you could always write tangent as sine over cosine and do a u substitution. We've got minus and negative, so just to clean up my answer here, I'm going to go ahead and change it to addition. So I've got 1/2 tan squared x plus the natural log of the absolute value of cosine x plus c. The very last one I want to show you in this section is a good example of what to do when you just have no idea what to do. So we want to find the antiderivative of cosecant squared over cotangent cubed. Cosecant squared over cotangent cubed. There is a very straightforward way to do this with cotangents and cosecants if you get good with your derivatives and your u substitutions. But just as an example, if you get a problem that you have no idea how to do it and it's got trig in it, remember back from your trig class that all of the trig functions can be written in terms of sine and cosine. So if you ever get stuck and are not sure what to do, you can always change everything into sines and cosines. So that's what I'm going to do for this one. It isn't necessary for this one, but just as an example so you can see one. So if you get stuck, try changing everything into sines and cosines. And we'll see how that works on this one. So we need to remember from trigonometry that cosecant is 1 over sine. So that's how I'm going to rewrite my numerator. And then cotangent is cosine over sine. And instead of having a fraction divided by another fraction, to simplify this, we will flip and multiply. And you always flip the bottom fraction. And you see a bunch of our signs are going to cancel out. I can cancel out sine squared with 2 of the signs from the top. And what we're left with is the integral of sine over cosine cubed. Now both of these powers are odd. If you have a fraction, you should always go with your u in the denominator, because it's very rare that when you do a u substitution, the du will rarely ever allow you to cancel something from a denominator. The du usually brings in something to the denominator, which will then help us cancel out something from the numerator. So usually we're going to let the u be what is ever in the denominator, and we only need it to be one of them. We don't need it to be all three. It's perfectly fine to have that cubed stay. Remember, cosine cubed x is actually a composite function, cosine x with a cube on the outside. And with composites, we only need to let u be the inside of it. So if we let u equal cosine, du is going to be negative sine x dx. And if I replace a chunk like I did before, I've got sine x dx. I don't have negative though. So if you want, you can divide that negative over to the other side so it comes back in with your du. And now this is going to turn into the integral of 1 over u cubed negative du. And that negative is just a coefficient we can move to the front. And then u cubed, we're going to have to bring that to the numerator as a negative 3 power in order to integrate it. And now it's just a power rule. So we add to the exponent, we're going to have u to the negative 2, and then we flip that exponent as a coefficient. And we already had a negative, so we end up with a double negative there. So I've got 1/2 u to the negative 2 plus c, and our u was cosine. Now, this format of writing your answer is not usually the best format. Trig functions don't ever have to be left in a denominator, and that's what that negative power means. This is technically 1/2 of 1 over cosine squared. That negative power means move it to the bottom. And cosine in the denominator is a different trig function. It's equivalent to secant. So probably the best answer here would be 1/2 secant squared x plus c. We probably would have gotten the same answer if we had done it the other way. Well, the other way was cotangents and cosecants, so it's possible it could have come out a little bit different. But because of all of the trig identities that we learn, there are a lot of equivalent answers that would be acceptable to these problems, including in MyLabs Plus. It should be able to tell that it's an equivalent answer, just depending on which way you decide to solve it. So you could always, if you get stuck and have no idea what to do, change everything into sines and cosines and then just follow your sine cosine rules.